Good morning, everyone. Welcome to Data Tech Talk for LinkedIn's TechCon 2022, powered by Women in Tech. Thanks to each one of you for being a part of it, and I hope you're having a good time exploring the networking booths at the conference and the different sessions that we had yesterday. I look forward to seeing you today as well after the session at the networking booths. I am Anirban. At LinkedIn, I'm a part of the engineering team that works on predictive machine learning, helping improve the life cycle of ML models in LinkedIn at scale. Let us talk about the agenda for the day. First up, we'll have an overview of the data and infra platforms at LinkedIn by Hari Kumar. We'll follow it up with an overview of Darwin at LinkedIn by Balamurugan and Hari Kumar. Post this, we'll have Varun and Srini take us through the big data and compute storage at LinkedIn, and we'll wrap up the session with a Q&A. A quick note to the audience, please feel free to drop in your questions in the Q&A tab of the chat box on the right of a viewing panel. We'll answer all of your questions towards the end of the sessions. Over to you, Harikumar, for taking us an overview of the platforms and data infra at LinkedIn.
All right. Thank you, Anirban. Good morning for the session overview. What I plan to cover today is to talk about the overall data infra and platforms that powers all our product that we have at LinkedIn. So one of the things that you would have heard about through the tech talks yesterday and today is the amount of data, the scale of data, the scale of interactions on the data, and all the aspects that the products finally get to cover through the power of data, right? So this is a slide which kind of covers what the data life cycle at various stages of the LinkedIn products is, and more importantly, through the varied interactions from our members and through the entity graphs that these data generates, right? So overall, to just give an overview of the scale of the data, we have around 810 million members in the graph, generating a lot of actions, content, job posting, company pages, events, etc. So the graph itself is around 1 billion entities plus, and growing at the rate of 30% year on year in terms of the conversations, public conversations that are being had, and all of that. So the network edges of the graph is even more complex, is around 240 billion, right? So in the data infrastructure and platforms group, what I want to show is this life cycle translating itself to the various components of the data stack, and through this also walk you through the complexities involved in the various platforms and how they interact with each other, right? So the slides that I'm going to talk about is an overview of the overall tech stack, mapping to how from a product the member actions get ingested all the way back to the serving layer, right? That's what I have planned for the overview session. And post that, we have two such platforms being deep dived into. One is the data science and AI platforms, which is the workbench that all our data and AI engineers use to overall the exploratory data analysis phases of this insight generation cycle, right? And then we have one talk deep diving into the big data compute and storage aspects, the complexities of some of the problems that we are solving. So I'll start with the overview right now. So what you saw in the cycle in the previous slide, starting from data generation through these points. So any typical modern data infrastructure stack will have some of these components already called out, right? So you start with the data and transport all the way from tracking through these products. It could be the mobile app, front end, web front end for these. So the tracking infrastructure, the transport infrastructure, and the overall data ingestion infrastructure is what is on the left. So remember, all of these that I'm talking about, uh, most of these are open source projects by LinkedIn. Kafka is the ingestion and the transport infrastructure. Data ingestion is the goblin. So a lot of these are already detailed blogs are available or in the process of becoming open source. I'll talk about that a little later. So yesterday in the AI session, you would have seen a lot of stress on productive ML, and the ML infra team is focusing on simplifying various aspects of model authoring, model training, model deployment, and the serving and inference layers. Right. In the data infra layer, we have the unified data lake, which has the again, to give you a perspective of scale, the size of our infra is closer to exabytes, the data lake itself, and the cluster sizes are around 25k nodes, right? Just to give you a perspective of the number of nodes that the data lake infra team needs to operate and manage this massive data flowing into the data lake. And post that, there are a lot of infra components or platforms which deal with specific parts of the derived insights layer, right? For example, the graph infra, the search infra, they deal specific to serving the search for the products, or the graph is where all the massive network graph kind of queries are served, right? So yesterday you heard Malai talk about how some of this, the graph infra itself, is going to become a key Azure offering, and because something at this scale at a graph infra is not available in some of the offerings that Azure has right now. So this is becoming a business in itself, right? And Pino, for example, is our OLAP engine. Pino serves a lot of the analytic layers, both for internal metrics as well as some of the site-facing insights that are delivered on the analytics that are delivered through some of the products, right? So the lowermost layer, the data management, is a significant problem because of the varied amount of platforms that they need to deal with. Let us take the example of metadata platform itself. So the problems of discovery, global insights, global lineage, the compliance, metadata applications like, for example, detecting duplicate across metrics, cost attribution across all of this for one particular feature. The feature goes through, say, raw data transforming into features getting extracted from features model to final some of the apps or services serving the inference layers, right? So this entire lineage and through this entire transformation process, there are a lot of workflow components that are kind of transforming data. Some are basic workflow pipelines using Spark, TensorFlow, or some could be very specialized metric pipelines which translate these to metrics, right? So capturing the global lineage across all of these and the operational data for all of this becomes a big challenge because of the varied amount of platforms and components that you see on this, right? And this is only becoming more challenging for us, primarily because as you LinkedIn, the entire infra is moving to the cloud. So as this transition happens, this stack will get new components added, either through some of the available stores on the Azure platform, as well as the overall components integrating neatly into the cloud native stack, right? So because of this, the layer below, which talks about the entire aspects of metadata, data observability, quality, and the privacy and compliance becomes so much more challenging for LinkedIn. Right? So the final layer on the right is where the serving layer happens. It could be via, let us say, you talked about the model cloud APIs on and the serving layers. Yesterday, we saw that, or it could be the data science platform, which we'll be covering in a subsequent slide, covering a lot of uh, insights all the way from the exploratory data analysis till delivering insights in the form of dashboards and apps, right? Custom built insight apps, right? So this life cycle is trying to capture the overall overview of some of the platforms. Now, one theme that unites all of this is these are loosely coupled systems which needs to unify finally to deliver one feature, right? It could be, yesterday in the AI slide, you talked about the search relevance, right? So that is one feature which hugely powers some of the uh, product features on the site, right? So that is a combination of features, heavy ML models, both at the ranking and serving layers, using some of the data from the data lake, and the search infra itself is a big problem, as you saw yesterday, in terms of the scaling and scaling re-architecture of some of the shards and all of that, right? So this unification of this loosely coupled platforms across the entire uh, stack is one theme that continues to happen at every layer, right? Be it the metadata layer, be it the data science platform layer, the data observability layer. So these are some of the things that you will see in the subsequent slides that we have planned today, right? So just to give a quick overview of some of these aspects of the platform work happening in Bangalore, the highlighted ones are teams which are directly contributing to these components of the platform based out of Bangalore, right? So the reason I put this up is also indicate the amount of spread in terms of the data platform stack across geos, and how some of the teams here are actually contributing to uh, the platformization efforts at scale, right? The ones which are in dotted are teams which are growing in Bangalore. So this gives a good overview of the data infra and platforms groups in Bangalore. So with this, I will hand it over to Bala Murugan, who will walk us through the data science and artificial intelligence workbench at LinkedIn. We call this Darwin. Over to you, Bala.
Thank you, Hari. Hello, everyone. I'm Balu. I'm very excited to give you all an overview of Darwin. So Darwin is a unified platform for exploratory data analysis at LinkedIn. It's a single window for all data explorations here. Darwin provides a Jupyter-based notebook interface, as well as it provides our own proprietary SQL workbooks interface for some of the use cases that are required. So Darwin is used by various personas here, like data scientists, data analysts, ML engineers, AI engineers, etc. So some of these use cases require a variety of access to engines like Spark or Flink, Hadoop, Trino, etc., which Darwin enables, as well as access to a lot of open source and in-house tools and libraries. For example, TensorFlow, Scikit-learn from open source, and other libraries like Frame, etc. Internally. We also offer a choice of languages, be it Python, R for data scientists, or SQL, Scala, etc. For some of the other use cases. So we also integrate with various other internal tools to unify all these workflows. So in this diagram here, we are looking at the platform view of Darwin. So the platform foundation is built on top of Kubernetes, which provides a scalable layer for us. It also enables our users to customize it heavily to meet their specific use cases without us being in line. And we have additional capabilities part of this foundation layer, like authentication and authorization, governance capabilities like auditing, version control, etc. On top of this foundation, we have built this layer for iterative analysis that is powered by our notebooks and workbooks. Again, like you mentioned, there is a choice of languages here and other integrations that we do with internal tools that enable users to iteratively create their analysis. Post creation of these analysis, they can distribute it, be it in the form of reports that can be scheduled to be updated at a frequency, or even deploy them as interactive apps for live data interaction use cases. Let me talk through a very high-level architecture overview here. So we, like I said, use Kubernetes underneath. So we spin up user pods, which are dedicated to the user using Jupyter Hub, which is another open source project. And we use our Azkaban task manager for also creating pods for non-interactive use cases, for example, scheduled executions, etc. As can be seen in this diagram, we do interface with a lot of big data systems here, thus unifying a lot of workflows for our users. So I'll now briefly talk about how Darwin is used by some of the personas here at LinkedIn. For example, data analysts, data scientists, etc. I'll start with data analysts. Data analysts prefer a very simple interface. They often create queries and execute them against Trino or Spark and analyze the results and visualize them, etc. So for this, we offer SQL workbooks. Underneath, although it uses the Jupyter kernel protocol, it provides a very different interface and a lot simplified interface compared to notebooks. So using this, data analysts can author their queries and they can analyze the result using a very powerful and optimized front end that we offer. So unlike tools like Excel, etc., where users may be limited by the amount of data they can analyze. So here, they can analyze large amounts of data because of the optimized interface, as well as the caching layer that we use in the backend to power some of these cases. So a representation of the result data frame is held in this caching layer, and the queries are performed on that post the initial query. So that is very performant. Plus, of course, there is leverage of big data engines like Trino and Spark to analyze at big data scale. So our data analysts also can, of course, leverage the tabular form grid here to perform typical grid operations like search, sort, filter, etc. Plus, also they can create pivots on these results or create custom visualizations on the results without writing any code. Let me now move on to the next type of persona that is that uses Darwin. So data engineers also have a very similar workflow as data analysts, but in addition, they also take these mature queries to create their UMP flows, which is basically to create their metrics. We also integrate seamlessly with an internal metric authoring tool, which can be leveraged by our users in a seamless one-click way. Let's now look at how data scientists use Darwin. So data scientist use cases are very stats heavy typically, and they perform operations, excuse me, sorry. So they perform stats heavy operations like trend analysis or testing of hypothesis or correlation and causation, anomaly detection, etc. Right. So a lot of these use cases are best met with notebooks. So we do offer notebooks in various languages like Python, Scala, R, etc. Plus, data scientists also prefer to work with a lot of open source libraries to create their analysis or custom visualizations. So we bundle a lot of these popular open source libraries as part of the Darwin. So once data scientists create their analysis, they can share it with their consumers. Um, of course, there is control of what needs to be shared, who can view outputs, etc., and all those audited. As well as data scientists have capability to share a report view that is very different from a notebook view. So often the consumers of these analysis don't need to know about the complexities of the code involved or some of the intermediate steps involved in creating the analysis. So data scientists can, in fact, create a custom view, controlling the layout and content, etc., and share this customized report with their consumers. In fact, these analysis can also be checked into Git and version control there, follow the typical review process, as well as have it scheduled for periodic updates. Let's now look at how ML engineers use Darwin. So again, ML engineers follow similar workflow as data scientists. Plus, in addition to performing the data analysis, they can also create models, tune their models, and perform feature engineering, etc. So once their model is, initial model authoring is done here, of course, they can use other frameworks that we have and eventually productionize it using ProML, which is our internal framework for deploying the models. So now I'll hand over to Hari back to talk about Darwin model.
All right. So what we want to cover in this slide is to walk you through the journey of how the platform got incepted, right from so whatever you saw, all of this happens based in Bangalore, right? So we took a three-pronged approach, three pillars as we call it: the product approach, the platform approach, and the partnerships, right? So when we initially started off with Darwin, the request was, can we get a notebook up and running within LinkedIn, right? So notebook infra up and running within LinkedIn. So when we looked at the broader industry trends and the market direction, a lot of folks were taking a broader view across what they call as the data science platform. Gartner, for example, tracks this as a vertical now, the data science platforms, right? So when we looked at some of these and we spoke to our customers, so by the way, we engaged directly with a lot of our customers in different formats, right? So we formed what we called as a user council. From there, we also validated some of the approaches and asks, and clearly what was standing out was to differentiate the product features from the platform features, because a lot of these unification differs across, like you saw in the overview slide for the platform, there is a lot of platform stack components that we needed to unify, right? So and this area was fast evolving, right? So a lot of new libraries, a lot of new techniques, a lot of new approaches being and so in the process we built strong partnerships with the different teams. So we closely work with the infra teams, we closely work with the Kubernetes team. In fact, our application was one of the first to go live on at scale within the Kubernetes within LinkedIn, right? So this life cycle, the end-to-end product life cycle and platform engineering is something that the engineers get to do, working closely with customers, and in the process unifying all of the complex platform components that you saw in the overview slide. With this, I will invite Varun and Srinivas, who are part of the data infra group, to talk about the scale and challenges that they solve in the compute and storage layers. Over to you, Varun.
Thanks, Hari. Thanks for the great talk, Balu and Hari, on Darwin. So this is Varun. I lead the compute platform team here in LinkedIn Bangalore. My team is responsible for the tech behind one of the largest offline compute clusters in the world. In this talk, I'm going to talk about how we scale our compute clusters, make our compute more performant, and solutions we build to understand what's happening in our clusters under the hood. And later, Srini would cover data compliance and how we provide mutable data sets in our data lake. So as the slide shows, so when we talk about scale, let's see the numbers of what that means at LinkedIn. So while Hari touched upon it, let me reiterate. So we have our offline clusters spanning over 25,000 nodes, with the largest cluster being around 15,000 nodes. We launch hundreds of thousands of offline jobs daily, ranging from big data analytics to machine learning jobs. In fact, no other figure gives a better sense of magnitude of scale at LinkedIn than our data lake storing over 2 exabyte of data, which in turn powers several solutions at LinkedIn. So next, I'll talk about how we scale our compute clusters through Robin. So in LinkedIn, we run our compute on top of Hadoop Yarn for most of our batch and machine learning workloads. We have also started using Kubernetes for some of our deep learning use cases for the last couple of years. Both Yarn and Kubernetes are compute orchestration and resource management platform that manage compute, which is essentially CPU, memory, and a few other resources spread across multiple nodes, with the aggregate compute represented as a single logical entity called cluster. So it is the cluster to which offline jobs are submitted to, which is like you have a single place where all of this compute is available. These platforms also schedule and launch job fragments across these nodes in a distributed fashion. Architecturally, both have a single leader and multiple agents running on each node, just to give you an overview of how this works. In Yarn, resource manager is a leader and node manager an agent, while in Kubernetes, the corresponding things would be API server and kubelets. However, a single Yarn cluster does not scale well beyond 10,000 nodes, which does not work with the scale which we have at LinkedIn. Kubernetes does not scale beyond even lesser number of nodes, somewhere around 5,000. Keeping this in mind, we set out to build Robin, which helps us horizontally scale our compute clusters. Robin essentially is a load balancer that can dynamically distribute jobs to multiple Yarn clusters under the hood. We decided to split our largest clusters into smaller subclusters while them continuing to be a single logical entity behind Robin, to which jobs are submitted to, as you can see in the diagram. These Yarn clusters share the same underlying HDFS cluster, and what we had to do is was to have rack striping to ensure that there is data locality, if not at a node level, but at least at a rack level, which worked well for us. While Robin is currently deployed for Yarn, it is designed to integrate with Kubernetes as well, as you can see in the picture. And it will be used to scale it once we reach scaling limits for our KDS clusters. They are just starting out, so the number of nodes in our KDS clusters are somewhere around 1,500 to 2,000. Robin also allows us to extract away details of the underlying clusters and even the compute orchestration platforms, providing a unified resource management layer, allowing us to innovate under the hood in future. Next, I'll talk about some of the changes we have made in Yarn at LinkedIn. So before we begin, let's talk about what Yarn queues mean. They are the fundamental unit of job scheduling, that is job placement on various nodes in Yarn. We use capacity scheduler at LinkedIn, and each queue represents a percentage of cluster capacity. You can learn more about capacity scheduler on the Hadoop page. Jobs are submitted to queues within Yarn, and queues at LinkedIn are aligned to departments or orgs, with org queue owners responsible for managing capacity and other configurations for their queue. As you can see in the diagram, that is done through a self-serve UI. What we do is users in LinkedIn are automatically mapped to a queue based on the org they belong to, which is retrieved from LDAP. This helps us distribute capacity between orgs and attribute cost to them as well in return. In LinkedIn, users typically submit workflows represented as DAGs via Azkaban, as you can see on the top of the diagram. Each node in the DAG may represent a job to be executed on the Yarn cluster. Azkaban then integrates with Robin to decide the right cluster job has to be routed to. So that's how we achieve the scale which we do. As users typically submit flows, one of the other things which we built was workflow priority to prioritize some of the critical workflows which are there in our ecosystem. Queues in Yarn also have hard and soft limit, which are called guaranteed and max capacity. If free cluster resources are available, queue can expand up to max capacity. But these configs are static. So what we did was that we developed something called an elasticity tuner, which helps us dynamically change max capacity to handle burst load in a queue. As the graph, which is on the right-hand side of the picture, shows that it helps us achieve higher queue usage and lesser queues delays. We also persist these queue configurations, including the changes made by queue owners, so that they are available across restarts. All of these changes which have been made have been also contributed to Hadoop, and our teams regularly contribute to open source, not only my team, but various other teams across LinkedIn to make all of these solutions even better. So next I'll talk about how we test at our scale. So at such humongous scale, it is always difficult to predict whether a change would impact performance when deployed. So this is where we set out to build something called Dyno Yarn to simulate changes for yarn at scale. So Dyno Yarn can be used to bring up arbitrary sized yarn clusters, single or multiple behind Robin, utilizing a very small fraction of the overall capacity of the cluster. So for example, if you're launching, say 10,000 nodes, you might be barely using 100 nodes on the existing yarn cluster. As I talked about, we leverage yarn itself to achieve this, wherein we have a driver and a workload app. So the driver app is responsible for bringing up this fake or dummy yarn cluster, and while the workload app is used to run the workload traces from production. So that helps us simulate whatever we are doing, so as to speak, means to simulate whatever is happening in the real production cluster and test out our changes against it. We have open source Dyno Yarn, and you can learn more about it in its GitHub repo. It should be easy to find. Next, I will talk about Spark at LinkedIn. So Spark is the most popular compute engine at LinkedIn, and currently most of the compute is occupied by Spark jobs at LinkedIn. As some of you would know, that Shuffle is the most expensive operation affecting Spark job runtimes. In LinkedIn, we perform tens of petabytes of Shuffle every day. And this in turn posed immense challenges with IO and network bottlenecks with plain vanilla Spark Shuffle, which is provided in open source. This led us to build Magnet, LinkedIn Spark Shuffle solution. Magnet is a push-based shuffle solution where shuffle blocks are pushed to remote shuffle services based on shuffle partition, and then they are merged there. Driver, the Spark driver I'm talking about, manages the merge, all of this merge operation. And with merge shuffle files, we have been able to improve IO efficiency due to large sequential IO instead of small random IOs happening. So driver also considers data locality of these shuffle files while launching reducers. All in all, Magnet has helped us reduce fetch wait times and have also reduced job run times by over 26%. More details can be found out in the Magnet blog. Apart from this, we are also moving towards Spark 3, and it is gaining prominence within LinkedIn with features such as adaptive query execution. And we have also invested in scaling Spark History Server because we have so many large number of apps which are being launched by supporting distributed SHS. Most of the work, including Magnet and some of the work which I talked about above, has been contributed back to the Spark community. Next, I will talk about how we deliver insights through operational data warehouse at LinkedIn and how we deliver big data insights through that. So when we work at such a scale, getting operational metadata in itself becomes a big data problem. It's not necessarily some small number of metrics. Operational data warehouse is a data warehouse containing a collection of metadata, operational metrics, and events from various platforms, which are there in the big data ecosystem, as you can see. We consume Kafka events, scrape data through Spark jobs, and integrate with various platforms such as Goblin, which is the ETL framework of choice in LinkedIn, to create this data sets, all of these data sets which are there in the data warehouse. This rich information powers several use cases, such as debt flow analysis, which is flows whose output nobody is consuming, cluster peak reduction for cluster optimization, as the cluster peak actually drives cluster size and hence the cost of compute. This also includes the cluster Peak reduction also includes creation of flow provenance graph, wherein we capture all the context regarding a flow, which is the Azkaban flow, what are the executions, what are the dependencies in terms of data dependencies, inputs and outputs, so that we can find out that when the job should actually run. The operational data warehouse also powers Spark failure analysis, which I'll talk about a little bit later, and even cost attribution. ODW datasets are queryable, and users can write complex queries to answer various other questions, such as why my job is running slow as well. So next, I'll talk about some of the sources from which ODW or operational data warehouse ingests its data. So as you can see, ODW gets its data from Azkaban, which includes flow lifecycle, job lifecycle information, even project permissions, Yarn app and queue information, data from various compute engines such as Spark and Trino. And it also integrates with platforms such as UMP, which is our matrix platform, which Hari touched upon earlier in the initial slide, and Goblin, which is an ETL framework. So all of this data helps us capture a good view of what's happening under the hood operationally in the big data ecosystem at LinkedIn. So next, let's talk about some of the key capabilities of ODW. So as I said, ODW provides rich metadata about various entities in the big data ecosystem. The data can be queried from ODW. So ODW provides joinability across entities, which makes it very, very powerful. We also have second order data sets, which are essentially views for commonly occurring use cases, so that folks can avoid joins, right? Means these are common queries. You don't need to waste a lot of time in sort of creating queries again and again and have repeated joins. The low latency of data ingestion also makes it serve near real-time use cases, such as alerting on failure whenever possible. Next, I'll talk specifically about Spark performance, which we achieved through Gridbench. So as I said, Gridbench allows for application performance analysis. It answers questions such as, why is my Spark job running slow? Why did the runtime vary across different runs? So we can have one run of a Spark job and another run of the same Spark job and compare how the metrics and how the various things have changed. What is the resource usage across the runs, and things such as that. What we want to achieve in future is to be able to do root cause analysis for job failures automatically. We also want to provide real-time recommendations to prevent failures in future, as in these are probably the configs which you can change. And in future, also auto-tune Spark jobs to detect failures in the future and correct them. So these are some of the capabilities which Gridbench is going to provide in future. With this, I am going to hand off to Srini, who would cover data compliance and how we provide mutable data sets in our data lake. Thanks.
Thanks, Arun. I am Srinivas. So I manage the storage charters in Bangalore, and I'll talk about a couple of the key areas which we invest on from Bangalore side of things. So one area is data compliance. So when you talk about data compliance, we are talking about the data regulations, right? So we have GDPR in Europe, we have CCPA in the US, and various upcoming data regulations. And we basically work on implementing those data regulations at scale in the offline world. So let's take a quick view at what a data privacy look like and what is PII, which is the most common term. So PII is any form of personally identifiable information which we want to make sure that it is kept private for any kind of consumption. And typical examples of PII is the email IDs and logs and things like that. I have kept few of them here, but we have more than 52 of variations of that being identified and classified as PII. Next, I will talk about the core of how we solve this compliance problem. So, if you really look at it, we are really talking about compliance transformation, and the transformation can be in multiple side of things, but largely it is this, right? So, if you really look at it, we have the metadata. So, Hari talked about the metadata systems, which has the details about what is what, right? So the annotation saying that certain data is compliant. Then we are talking about the query context, which basically saying that how we are planning to use the data. So this could be advertisement, this could be data science use cases, this could be reporting use cases and things like that. And third is the privacy setting, which is largely how the user says that they want their data to be used. Some user can say that I want to use it in whatever way you want it, or some people can say that you have to be very cautious about how data is being used. So if you look at a normal flow of a typical read cycle, right? We do the table scan, we do the filtration, and we do the select operation. But when it comes to the compliance version side of things, we basically add a compliance transformation also in that loop, which will basically do either anonymization in the case of obfuscation, or if you want to keep the data private, to filtration when you're talking about delete. So this is kind of the overview of how the core of how the compliance logic is being driven. But this manifests itself in multiple forms, right? So when you talk about anonymization or obfuscation, the way we earlier used to do is we basically take this concept and apply it at scale at all the data which is being generated in LinkedIn, and create a separate cluster out of it, and then that cluster is what everybody has access to. We are moving away from that approach, primarily one because there's a lot of cost in maintaining the two version of the data and also latency requirements. So the current approach is to basically apply this compliance transformation inline when the user accesses it, but then it has its own challenges of we are basically putting the transformation right when people accesses the data, but it has a very low latency, and also it works really well from a cost point of view. So that is one kind of a journey which we are also doing from a obfuscation side of things. Next, I'll talk a little bit about how the compliance transformation in its own works in an end-to-end system, right? Just to give you an overview of how a typical implementation looks like it. So we are currently looking at a delete side of things. So if you look at it on the right hand side, we have a lookup table being built. So roughly, this is this is basically the list of a contents list of the accounts which needs to be deleted. If we take the case of account closure delete use case, we take that, and on the other side we have the storage power data hub, which gives us the actual list of files or data sets which needs to be deleted, and the annotation respect to that. And then we have two kinds of purges. So one kind of purger is where the compliance transformation typically works, where we basically find out all the records of the account which needs to be deleted, and we basically delete it. Again, delete can be a filtration operation if it is a retime, or it can be a rewrite operation if it is a kind of hard delete. And second kind of delete is limited retention, where we don't need to do a row level filter kind of a delete. We basically so if you have a transient data and the data is not going to stay beyond 30 days, we basically go and delete it as is, and we leave it to the user to basically choose what kind of delete they want. But either ways, from a compliance side of things, we are compliant. And of course, the key element is the last thing we want to follow is the monitoring aspect, because everything we do compliance, making sure that we are indeed compliant, that showcasing that from an audit point of view is very key. So that's where the last bit of it. Next, I will quickly cover Opal. So that's the second area which the Bangalore team is responsible for. So here the problem we are trying to solve is how do we ingest mutable data from databases to the offline world at a low latency at scale, and that can be used for further processing, or can be used for reporting and other things, right? So typically, as you know, like an update and insert, etc., is very cheap in MySQL and Oracles, but very hard in HDFS. So Opal is again, earlier we used to have a different ways of solving problem. That's called Lumos. And the way Lumos kind of solves the problem is basically, we have a base snapshot, and then whenever we have the changes, it basically merges that and create a new base snapshot, and base snapshot has the latest copy of the data. The problem is that it has a problem of write amplification. A small change can lead to a lot of rewrites, and also, providing a solid latency, or to say that okay, we will have an SLA of this is very hard, because it's very hard to time the operation. So we introduced a new format called Opal. So Opal solves this as a read filter rather than rewriting the entire data. So we basically ingest the data, but we also keep a metadata of what is the versions of the thing, and we know that these are the versions of the same data, and this is the latest version, and that is where the Opal metadata comes in. And so when an insert happens, we basically append it and update the metadata, and when the read happens, we basically know where is the latest, and we use that. The reason I used the word filter rather than Latest is because while most of the people want to use the latest data, there are some data science use cases who want to have a point in time, so they can actually go back in time and look at it to kind of say, I want to have data as of this day to basically match the machine learning models performance. And of course, we also have a background slow running compaction, which will basically make sure that after beyond certain retention periods, we also clean up the data. So it's not an infinitely growing thing, but we do keep the versions to also handle it. So it's kind of a trade-off between that. We did publish an engineering blog on Opal, so please do take a look at that, and feel free to leave your comments, and we'll be happy to hear your thoughts on that. So with that, yeah, we covered it. Yeah, so over to
Yeah. So guys, yeah, so feel free to post your questions in the Q&A link, chat box you would have got. So as we wait, so this is a question for Hari. So what is the USP of LinkedIn's infra and data platform when we compare to the similar enterprise platforms or the open source ones?
All right. So, see the USP. So LinkedIn is at a time where the scale and the factors like moving to the cloud right now is one of the biggest challenges as a infra group that we are currently addressing, right? And all of this without disruption to the business is something that needs to happen, right? So you saw how unification of these disparate platforms is one of the themes, right? So ensuring that, let us take the example of Darwin, right? So while uh, this problem of providing a easy way to uh, for our data scientists and AI engineers to do EDA is a bigger problem. But subsequent to that, integrating with all the other existing components in the stack, right? So one of the personas for Darwin is to do metric authoring, right? So do they just do uh, authoring using the Darwin platform and then copy paste all of that again in a different product, or do we provide the seamless experience of saying that I've done this, promote this metric to production, right? So that's where each platform's focus is, right? How do we seamlessly integrate with all these other components and at the same time be open for extension, right? So what do I mean by open for extension? So right now in the Streams Infra group, Samza has been the heaviest infra that is being used so far, right? But the Streams Infra is also kind of experimenting and piloting Flink, right? Which means all the underlying systems across the stack, including the metadata platforms, including the catalog systems, including the Darwin kind of needs to ensure that we support the same experience as for Samza with Flink, right? So that is the unifying theme across all of this. I would not call this as an USP. This is a problem that every platform needs to solve for, right? While independently each component is focused inwards in terms of solving scales, solving the usability, productivity issues, all of that. This unification across these loosely coupled platforms is a big problem that the entire data and platforms group is set out to solve cleanly.
Yeah, I'll also add on to that, Hari, if you're finished. So, in addition to what Hari said with regards to uh, that we require unification of disparate platforms, some of which may not even exist outside. What also is true is that many of the enterprise solutions or cloud solutions do not just scale. We are talking about maybe new companies just coming up and maybe setting up a 500 node cluster and so on and so forth, while we work at the scale of around 25,000 nodes right now, and the compute scale and the storage scale continues growing at the rate of 70 to 80% per year. So this scale is something which is not available off the shelf in many of the enterprise solutions which are there outside. You have to make it work. And that's where many of our teams make it work. Means even in future, if we ever move to cloud, it would be primarily infrastructure with our platforms existing because the other platforms just do not scale. However, all of these companies, including ours, with some of the other companies which are there in the ecosystem, do use open source technologies, and we continue improving open source as well. As I mentioned in some of the slides, we contribute to Hadoop, we contribute to Spark, and we continue contributing to various other open source solutions, wherein just the plain vanilla solution did not work. We had to improve it, we had to scale it, and we had to make it more performant. So that's where the utility of some of these teams come in. But yeah, I mean, USP in the end, because we work so closely with open source, after a while, these companies gain out of each other and we contribute it back to the community as well.
Good. Thanks, Hari and Varun. So next we have a question from Abhishek. This is for Balu. So how do you integrate Trino and Spark from SQL workbook within Darwin?
Yeah, thanks for the question. So, so our notebooks as well as workbooks can integrate with both Rhino and Spark. So as you may, if you've used Jupyter ecosystem, you may be aware of Magic. So for notebook use cases, we leverage that so we do provide Magics to interact with Rhino. Similarly, through Spark Magic and another subsystem called Libby, we enable interactions with Spark. So like I said, SQL workbooks behind the scenes uses the same Jupyter kernel protocol. So those two leverage the same code flow. So that's enabling both these access.
Thanks, Varun. Next, we have one for Srini. What are the process followed in LinkedIn while building data-centric applications or analysis that mainly involves leveraging sensitive data like PIA? So how does data compliance, works under that?
Yeah, so the key is the key aspect of there are two parts to the story, right? One is the data producer side of things, and second is the data consumers, right? So we have the data on the data producer side of things. We have a lot of both education and checks in places so that the producers of the data annotate the data correctly, and we have multiple levels of checks also to make sure that the accuracy of annotation is correct. And the second part of this, and of course, the pipeline is in the middle, and the assumption is that as long as the data is correct, our systems make sure that data is compliantly served. And the second part of the story is the users, right? So again, a different class of users have different needs from the data. So some use cases which has tie back to the user, tie back to the website or the flagship or the internet.com needs access to slightly more important data. So it goes in, there's a whole headset process in place to basically, they have to do this kind of business validation, and then there's a process involved in, getting access to that. And there's a kind of more common cause of people where, who has access to more of a component data. So yeah, we have a different set of process, one for the users produces the data to make sure that they are actually providing compliant set of data, and second is the consumer side of things. Also, we do the validation and the sign off, and they get access to the right set of data. And of course, from the middle part, which is actually the system which is producing this compliant data, we have a lot of audits in place so that the system is indeed doing thing and doing the right things. So that's kind of the high level summary of how we enforce. Happy to take any further questions.
Okay. So we don't have any more questions yet. So in case if you have further questions, you can directly reach out to the speakers to the networking booth. So now over to Anil.
Thanks for taking us through the questions and some amazing brainstorming discussions that we had. As we mentioned, if you still have more questions, we'd be happy to help you out in the networking booth sessions to have more interactive discussions around any areas that you would have. Again, at LinkedIn, we appreciate your feedback, and we would like to know what you love the most about these sessions and how we can improve more around this. You also have an option to opt in for a swag that you can fill up as part of the feedback. So we look forward to knowing in more depth about how you felt about the overall discussion. With this, we come to an end for this wonderful session. I'd like to take a moment to thank all of the speakers for taking out time for this discussion, and a huge shout out to the entire audience for taking out time and attending these sessions. I hope these were really eventful for you, and we look forward to seeing you again.